Hello again and welcome. Today we're going to be looking at the AMPROBE PM55A. This is a rebranded Brymen meter. So before we get started, a couple of things I'd like to show you. You may recall in one of the more recent videos I purchased this Fluke 189 to do some transient testing on, and I had mentioned that the case was in really bad condition. The plastic on this, or the rubber, had actually had some cracks and some gouges where it was missing some pieces. I tried to paint this, and of course paint doesn't adhere real well to rubber. I tried this stuff here from Plasti Dip. The first time I tried to paint it with this, I didn't use any primer at all, and what ended up happening is the paint actually tore away, so you'd end up with all these tear lines going down the paint. So I tried some automotive primer that's made for bumpers on cars. I wasn't too concerned about damaging this meter any further than what it was. Again, this case was in very rough condition. You can see here I started out with a dark blue, and it ended up just clashing really bad with the blue on the face. And again, on this meter the lens was totally destroyed. I ended up busting the original one out of here, and this one I handmade. I wasn't real happy with how this fit, and so I went back and I recut this with a Dremel tool, and now it fits a lot more like the stock meter. It's not too bad, you know, for a beater meter. Of course, it still fires up just fine. So there's really nothing wrong with the meter electrically. It's just mechanically this case is in really bad condition. So when I was painting the 189, I basically shot it over this piece of wood. You can see the dark blue versus the black. Again, this is kind of a rubberized paint. And when I first shot it, not using the primer, it peeled away from that rubber fairly easily. But since I put that primer on there, it seems to adhere pretty well to that stuff. So another project that I've been working on is a Labview interface for this 121GW. So while I've been working on this, I've also been working on a serial interface for this Unity 181A. I made a real short video about that recently. Basically, this is a Bluetooth interface. This is a part number UTD07A. The bad thing about this is Unity sold this under the pretense that it supported Windows, and of course they have no support for Windows at all. So again, I've been working on writing my own Labview interface for it. So I'll probably make a video about that software at some point. Again, it's still kind of in the development stage, so maybe in a few weeks I'll try to put something together. Again, this meter is sold under the AMPROBE brand. It's a part number PM55A, which is actually a Brymen BM27s. It's a 6,000 count meter. It has a display update rate of 5 Hz, so fairly fast, and it uses a single CR2032 coin battery. I follow a YouTuber named Voltlog. He put together a pretty good review of this meter. I suggest you check it out. I'll include a link in the description. So for this video, I'm not really going to be doing a review of this meter so much as just focusing on the electrical robustness of the meter. I may try to do my chemical test on it as well. I became interested in looking at this meter after a member who goes by the name of True out on the EEVBLOG site had posted about having purchased several of these that had a common failure mode. So back in August of 31st, 2018, this member, True, had written, a bit late, but I can say every meter man PM55 or AMPROBE PM55A I have has failed. What happens? Auto mode freaks out and doesn't work. A short shows an unstable high resistance, for example. Short detect mode shows shorted. EF power stick mode works. I can't remember what the low Z volts does. High Z voltage works. Diode mode acts like a short. High ohm varies from not working to usually sounding like the shorted beeper. Goes on to say high ohms will not give a stable reading. Haven't tested the current. It's kind of odd because the current mode I think on this meter has actually got a fused input. I know when I watched Voltlog's meter, it looks like there's 2 paths for the input. One's probably a drive side, but you'll actually see the one leg will have a small fuse on it and the other side is directly connected. He says he purchased a new unit after my PM55 had failed, only to find that a PM55 I gave to a friend also failed. I tested a PM55 I had and it too had failed. The replacement? Well, it tested good, testing 5 volts in the auto mode and shorting probes. That's it. After a month, when I went to use it to test a low voltage DC circuit again, it showed low battery, and sure enough, it failed too. I'd like to fix them, but I have no idea where to start or what could have failed. So another member, Retired Caps, had responded, so you're reporting that all these fail. And after you replace the CR2032 battery, it still doesn't work. True responds, yes, all have failed in the same manner. And of course I've tried the new CR2032 in each of them. The replacement batteries have all been fine, showing correct voltage with a resistive load. The screen on the meter has a sharp contrast and the low battery indicator is not lit. I believe there is some fault, but do not know what has caused it. I can only say that it has happened to all 4 meters that I have access to, and the meter that I bought to hopefully troubleshoot this failed before I really got to use it. Right now I'm hoping it's the MUX or SSR, and it may not be a low battery causing them to fail, but that's the only thing in common between all of them, is that they failed when the low battery indicator was on. Ruby Dust goes on, I checked the Brymen 27S. It has a legit 61010 UL certification, so it shouldn't be fragile to ESD. Of course, the 61010 has nothing to do with the ESD. That's the EMC standard 61326. I don't know if this meter is actually certified for that or not. It does call out the 61010 here, but yeah, I don't see, at least on the case, that it passes the EMC standard. But being a Brymen meter, I pretty much guarantee that it does. We'll check the manual when I get the case open. Not to blame the low battery, but that and non-harsh use are the only similarities, but perhaps the zip-up case they come in can generate enough ESD to blow something up. So I did respond to them. Basically, I was a little surprised because they had posted in the thread where I post where I test all these meters. I would have thought if they were looking for help on how to repair the meter, Dave's got a repair section that they would have posted out there. So I don't know if they were just trolling me, trying to get me to run the meter. I actually told them, if they want me to run it, just, write me and ask me, and, I would probably take a look at it. So after reading all this, that's basically what caused me to get interested in running this meter. So let's have a look at it. Again, this is brand new. I haven't done anything with it yet. Let's just see if it does meet the EMC standard. So looking in the manual, you can see on page 1, you talk about 61010-1. There's no mention of the 61326. On page 11, EMC meets all applicable requirements for IEC EN 61326-1. And having ran so many Brymen meters, I gotta believe that this meter would have been rated for that. It has a nice little pouch. I doubt that that caused any kind of problem with the meter. Looks like it powers up just fine. The switch has got a pretty nice feel. I tested a bunch of pocket meters and none of those really did very well in my testing. I'm not too surprised. I mean, you look at the size of these little pocket meters and, routing these where they would have enough clearance where things wouldn't break down. It's got to be fairly difficult. See, it's kind of nice. They have the instructions on the back of the meter. Again, here's the UL mark. So one viewer is asking about the physical size and how it compares against some of the other meters. Unfortunately, I don't save a lot of the meters I damage, and I don't have any of the original pocket meters that I tested. Once those meters get damaged, they basically get torn apart and they go to the recycle. These are some of the meters that I still have. On the left, this is made by Unity. It's the UT181A. To the right of this, we have the Gossen MetroHit Ultra Bluetooth. To the right of this, we have the Brymen BM27s. You can see that Brymen is just a little bit shorter than this Gossen, which is just slightly shorter than the Unity. Next to this, I have the Fluke 189. Again, this is the one that I just repainted. To the right of that, we have the Fluke 101. And then next to that, I have the Esd Test ZT102. So again, you can see this Esd Test ZT102 and the Fluke 101 are virtually the same size. You can see it's quite a bit shorter. It's a lot thinner. Obviously a lot lighter. I mean, look at this compared to this Unity 181. I And you can just see these meters are massive. Of course, this isn't something I would take into the field. The way I see it, these meters are really just kind of a portable bench meter. At least that's what I've been using them for. Personally, I still like this Fluke 101. With all the testing that I've put this meter through, this meter has never been damaged. Unlike these meters, I think I ended up buying 4 of these total when it was all said and done. I had one that was actually branded by Anag. I think it had a higher resolution maybe than this, and it had a pulse generator instead of the temperature sensor. One of the disadvantages people say with this Fluke 101 is that it can't measure current, you know, and I never really saw that as a negative. It's rare that I'll use a handheld meter like this to read current anyway. Alright, so you can see I have my test box out. We'll be using this to just conduct some real simple tests. I'll leave the meter in its auto mode, so I guess the way this meter works is it can actually detect what it's connected to. Let's start out with a 5-volt DC signal. And you can see it's reading 5.018. It's off a little bit, not too bad. Let's try it with an AC 2.5 volt square wave. Again, if this is a RMS meter, it's going to read 2.5, but if it's averaging, it should read about 2.78. Yep, so this is definitely an averaging type meter. I'm not too surprised. Let's try it with a DC bias. Again, this is DC coupled, so it's switching between 0 and 5 volts. So it sees it as a AC signal and not DC. So let's try it with a 0.5 ohm. This is with a 100 ohm. Wow, it's very slow to auto range. Let's switch it to voltage mode. I assume that this is in DC volts. Let's just see. Put it to DC. It should read 5. That's correct. This should read roughly 60 volts, but boy, you can see it's off by quite a bit. I'm not sure what's going on there. Maybe that loads down my test box quite a bit. Let's try it with our 2.5 volts AC. Yep, you can see it reads 0. Let's try it with the DC coupled AC. Yep, reads 2.5. That's what we'd expect. Let's switch it to AC. Yep. So now let's try it. Yep, 2.789. This again is our DC coupled AC output. Again, showing that it's an averaging type meter. This is the AC coupled AC output. And let's apply DC 5 volts to it. It should read 0. It does. Alright, this should be roughly 70 volts AC. Fairly close. And this is in Diode Check. Let's just try it with a dead short. Looks fine. This is a single diode. 2 diodes in series. Looks like it can't handle that. So let's switch it to ohms. 1K. That's an open. And 100 ohms. Let's try it in the auto mode. Again, this will be 100K ohms. So you can see in auto mode, it's actually able to read the resistance. But when you select the resistance mode, it's actually marked 600 ohms. That's probably the top end of it. Let's go back to auto and we'll try it with a 1 mega ohm. There you go, 1 meg. Let's try it with a 10 meg. Yep, we're outside of its range right there. So this would be current, and of course it has a microamp range. Let's just try 100 microamps. Looks pretty good. This would be 10 microamps, 1 microamp. The meter can't read capacitance or temperature or anything like that. It's a really no frills meter. Let's go ahead and we'll take this thing apart. So we just kind of peel the boot off. Looks like just a single screw on the back. Oh, coin cell just falls out. See, the contacts look really good. You know, and I'm not so sure that these are not the same contacts that are used in their higher end meters. It kind of makes sense that they'd just try to use the same part. Alright, so this is our input. and we can see it basically follows two paths. One goes up through this resistor, and we can see one spark gap sitting here. The other leg goes through this resistor and then up through this PTC, and right here is our fuse. I remember seeing that in Voltlog's video. You can see how the PTC is sitting here, and these two nodes here are connected right here, but this is the opposite side of the fuse. So look at the distance between these two. We can see the other side of the fuse follows this trace up along this around here. Notice all these high voltage slits they've got in the board. So it doesn't work real well, but you can see them all right here, here. There's some more down in here. Of course, at least from my test results, Brymen really knows what they're doing as far as designing for high voltages. All in all, it looks pretty impressive for a little handheld meter. I would say by far out of all the ones that I looked at, this one looks the most impressive. Of course, I had another meter that I tested. It also had a PTC, and I think it might have even had a MOV in there, and that meter didn't do very well. And that meter was also UL listed. So yeah, it really comes down to how the meter performs in the tests. One of the things I forgot to try was the EF detection. I'm just going to use my box. Oh yeah, no problems at all. So I was thinking about what True had posted, and that his batteries had died on the meters that had all failed. So I thought I'd try to find a dead one. This is one that was in a piece of equipment that I have, and I measured the voltage, and it was below 3 volts. So I checked the battery that was in the meter. This is the one that was supplied with it. So let me just show you the output voltage. So again, this is the Panasonic battery that was supplied with the meter. You can see it's reading 2.98, and this is an old one that I had. This is an Energizer, and you can see 2.98 roughly. So I thought what I could do is just hook this meter up to a power supply, so that's what I've done. I've just attached a couple of wires here. So my Brymen BM27s on the left is looking at the current going through the meter. The one on the right is looking at our voltage. So let's just go ahead and turn the meter on. See, it spikes up to about a milliamp. There's 6 milliamps. And then it looks like it drops to about 928 or so milliamps. I imagine that that's dependent on the mode that the meter's in. Of course, it's set to auto right now. Let's just try shorting the leads out. So what I'm going to do now is just go ahead and start reducing the voltage. You can see it's right on the edge right now. It's just a little bit too low. Let's just turn it up. You can see the battery symbol is being illuminated. So at 2.5 volts it's drawing roughly the same amount of current, about 920 milliamps. So I changed the current limit on my power supply. So now what's happening is once the meter powers up, it draws enough current where the power supply will start to fold back. You can see how the voltage drops, and then essentially that resets the meter, and then it just continuously power cycles. You can see the current gets up fairly high. Just set this to our min max. There's 3.44, 3445. So what I'm wondering is the battery begins to run down and the meter gets into a condition like this. Is that high current spike causing some kind of damage to the meter? Because the meter could actually be doing this without you being even aware of it. So what I'm going to do is just let it sit here and cycle like this. Alright, so this test has been running about 7 hours right now. I think what I'm going to do is maybe adjust the current limit down just slightly. Again, you can see the voltage changing. We're right on the fringe right here. You can see it's not powering up, but it's drawing about a milliamp right now. So what I'm going to do is just leave it like this for another few hours. Let's just see if this causes any kind of problem. Alright, it's just been sitting here for about 5 hours now. Looks like it's still roughly drawing about the same amount of current. Let's try to turn up the power supply and we'll see if it comes alive. Again, I'm just adjusting the current limit. Oh, There you go, fired right up. Let me just try adjusting it a little bit lower. Alright, so the meter's been running about another 4 or 5 hours. Let's just have a look. See, it's still drawing about 200 microamps. This is probably just the power supply drifting. Let's go ahead and turn up the current a little bit, and we'll see if the meter will power back up. That looks fine. Let's just see if it still reads resistance alright. Again, this will be a 1K ohm resistor. This is a 1 mega ohm. This will be a 5 volts DC. Let's try switching it to Diode Check. There's a short. Let's go to resistance mode. This will be a 50 ohm resistor. And let's just try current real fast. So, and this will be 100 microamps. So it doesn't appear that we've caused any damage to the meter. See, I'm not so sure that this problem that True brought up has anything to do with the battery being low. One of the things I thought I'd show you is this is a little crowbar circuit. I put this across the power supply. There's a pot on here that I can set the voltage, and essentially for long-term tests like this, if something were to happen to that power supply where it tried to exceed this 3.3 volts, this thing here will essentially just crowbar or short out the output of the power supply. Basically what I'm trying to do is save the load if something were to happen. As you can see, I have the ESD gun out. I'm going to be using this as a DC high voltage power supply. So I'm just going to attach these leads into these banana connectors. Like so. Alright, so let's just go ahead and we'll turn up the power supply. Again, they rate the meter for 600 volts, and you can see we're outputting roughly 570. The meter's reading about 580. Again, this meter is not very accurate. Let's try taking it up a little higher. Let's try it in the voltage mode. And there's 1,000 volts roughly. The low Z mode was just loading this power supply down a bit too much. But yeah, it doesn't look like we damaged anything. I'll go ahead and check it all out. Alright, for this first test you can see I have the transient generator out. Again, these leads are not detachable, so I'm just going to use a couple of alligator clips. We'll just clip right to the 2 leads of the meter. So for this first test we'll be applying a full rectified 220 volts AC. Again, this is unfiltered, and we'll do that with the meter in each mode. Let's go ahead and turn it on. See, it kind of confuses the meter. It's settling in on 114.3 volts AC. Let's go ahead and turn the dial. And here it thinks it's 227 volts. Let's just try it in AC mode. Yep, 114. Frequency should read 120 hertz. The meter probably can't read when the signal is above ground. It must need the zero cross. It looks like it's probably okay. Let's just do a real quick check. And this will be 5 volts. Looks fine. This will be 2.5 volts AC. That looks fine. Okay, so again, this is DC coupled, and you can see it's reading 0 hertz. So this is switching between 0 and 5 volts. This will be capacitively coupled, and this should be again at 60 hertz, and you can see it reads it just fine. So that's just the way that this particular meter works. And let's try resistance, so we'll go ahead and short the 2 leads. That's fine. Let's try it with a 50 ohm resistor. Yep, let's try it with 100. That looks okay. This is with a 1K ohm. Looks fine. And again, this will be 5 volts. Looks good. And this should read 2.5. That's good. And in AC mode, this should read 2.8, and this should read 2.8 as well. And let's see, in diode check, there's a short. And let's try a single diode. That looks fine. In resistance mode, this will be a 50 ohm. Looks good. And here's 100. Looks good. And let's try a current. And again, this should be 100 microamps. Looks good. Here's 10 microamps. Looks fine. So the meter seems to have survived that test. Next, what I'd like to do is use our Piezo grill starter. Again, we'll be applying 5 transients, both positive and negative, with the meter in each mode. Okay, here we go. And we'll reverse the polarity. Alright, let's just try it in the current mode. And this should be roughly 10. It should be 100. And this diode check mode with a short. And here's with a single diode. Let's try it in resistance. Again, this will be a 50 ohm. And here's a 100 ohm. Again, this will be 5 volts DC. Looks fine. And this should be roughly 2.5. That looks fine. Let's switch it to AC. 2.7 and 2.7. Let's go to auto mode. And again, 2.7. Switch it to DC. Looks fine. And let's try a 1K ohm resistor. Looks good. And here's a 10K ohm resistor. Looks fine. So yeah, the meter's probably okay. I think what I'd like to do is just spend a little bit of time and make sure that this thing is really functional, and then we'll bring out the ESD gun. Somebody asked me if I could run some RF tests on this. So I hooked this thing up to my RF generator and I did some sweeps up to about 500 megahertz. I didn't see any areas that this meter was susceptible. So I think what we're going to do next is perform our ESD test. So you can see I have our homemade ESD gun out. And again, because the leads are attached directly to the meter, I'm just going to plug this thing directly into the output of the transient generator. Again, this transient generator fairly closely follows the IEC standard. I made a video where I showed the output waveforms off of this, if you're interested. So again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. Let's just see if it's got a short. That looks fine. Let's see if it'll pick up a change for the diode mode. That looks good. Here's in resistance. Let's just try it in the auto mode. Yeah, it looks good too. Let me just go ahead and we'll functional test it. I fully functional tested the PM55A, so next we're going to start our transient test. Again, the leads are permanently attached to this meter, so I'll just be using these little adapters, and we'll connect the leads directly to the output of the transient generator, like so. So the last time I used this generator, a viewer had pointed out that when he looked at the oscilloscope, it looked like the generator was putting out 100 microsecond full width half height, but I kept saying it was 50 microseconds. If you go back and look at the documentation that I produced, that is correct. This does actually put out a 100 microsecond full width half height pulse, not 50. So yeah, if you catch an error like that, it's always best just to go with the documentation. That's correct. It's not that I'm changing the tests as I'm running these. There's a good chance I probably just misspoke if you caught something like that. So we're going to be starting out at 1000 volts peak with 100 microsecond full width half height with a 2 ohm source. We're going to be applying 5 transients, both positive and negative, with a meter set to each mode, and then we'll go back and functional test it. That's a little less glare. Alright, that's it. Alright, the meter appears to be still functional. Next we'll be applying a 1.5 thousand volt peak at 100 microseconds with a 2 ohm source. And this will be both positive and negative. 5 transients with the meter set to each mode. Again, when I had previously ran all these pocket meters, there was a couple of meters, one of them in particular, I think it was a Unity. I don't remember where that meter failed at, but it failed unusually high, especially for a Unity and being a pocket meter. So people interpreted that test that that meter was actually, more robust than many of the other ones I had looked at. Again, the problem with that particular meter was it was actually breaking down on the inside. There were just not enough clearances in that meter, so essentially you had these things that were acting as spark gaps, but of course they weren't designed to be that, and it would actually save components that were downstream. Had I hooked that to, say, this half-cycle line simulator, we would have lit that meter up. And unfortunately, that's what can happen with some of these meters. They could actually do better on this test, at least not get damaged, but that doesn't necessarily mean that the meter was, better than the other ones. So you have to be careful when you're interpreting the data that I'm collecting. Make sure that you understand what it is that you're seeing. Alright, that's it. Alright, so our meter pass is functional. Reprogrammed our generator to put out a 2000 volt peak transient. Again, this will be a 100 microsecond full width half height with a 2 ohm source, 5 transients, positive and negative. I can hear the spark gap inside breaking down. Just move the camera in closer, see if you can hear this. Didn't do it that time. I don't think you're going to hear it in the low Z mode. Alright, that's it. So I went ahead and functional tested the meter. I thought what we could do is take it apart and maybe see where things are breaking down at. Unfortunately, part of the problem with this is to really see what's going on, you almost have to have this thing kind of exposed. I can't have the LCD in there or the battery, but I'm not sure it's really going to matter. Let's just go ahead and we'll hook it back up. And let's see if this thing will break down without the switch attached. So again, this will be 2000 volts. I'm expecting it's breaking down in one of the 2 spark gaps. Yeah, looks like both of them. You can just detach the camera here, and you can see both spark gaps are firing. I don't see any other breakdowns. Let's just go ahead and I'll put the meter back together. I'll tell you one thing I don't like about this meter. Because of the way the case is designed, it would be very difficult to run any kind of test where I have the case open. It's not like most meters where the display could actually be mounted to the circuit board with the circuit board separated from the rest of the case. Same thing with the rotary switch. I think we could probably put that C-clip in there and it would be alright, but again, that display is going to be a bit of an issue. There again, you can see a dead short. Let's just put a 1 mega ohm resistor across it. There you go, 1.007. Again, this will be 100 ohms. And this is Diode Check, and of course this is a single diode. Again, this will be 5 volts DC. As you can see, we haven't done anything to the meter. And so because it doesn't appear like anything else is going on with the meter other than the spark gaps are finally breaking down, we'll go ahead and reprogram the generator. Okay, so I've reprogrammed our generator to put out 2,500 volts peak with a 100 microsecond full width half height. This will be with a 2 ohm source impedance, and we'll be applying 5 transients, both positive and negative, with a meter in each mode. Bring our test box out real quick. This will be a 1K ohm. Looks good. Again, this will be a 1 mega ohm. Looks fine. Let's just try it with 5 volts. Looks good. Again, this will be a single diode. Let's just try it with a 50 ohm. Just see about the microamps. So again, this should be roughly 100 microamps. Looks okay. I'll go ahead and finish functional testing it, and then we'll turn up the generator. I found ahead and reset our generator to put out a 3000 volt peak. Again, this will be 100 microseconds with a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with the meter in each mode. Alright, that's it. Let's get our test box out. This will be a 1 mega ohm resistor. Again, this will be 5 volts. That looks fine. You want to see AC mode. Again, this should be roughly 2.8. Looks good. And diode check. Again, this is a short. And this will be a 100 ohm resistor. And again, in current, this should be 100 microamps. Let's just try it in frequency again. This should be roughly 60 hertz. That looks correct. So it appears fine. Let me go ahead and finish functional testing it, then we'll set up for the next test. Okay, so the meter pass is functional. I've reprogrammed our transient generator for 4000 volts peak. Again, this is a 100 microsecond full width half height with a 2 ohm source impedance. We'll be applying 5 transients, both positive and negative, with the meter set to each mode. Let's have a quick look. Again, this will be a 1 mega ohm resistor. Looks fine. So here's our 5 volts. This is our 2.8. Should be our 60 hertz. And again, with the leads open, yeah, they're shorted. And again, this is a single diode. And here's a 50 ohm resistor. Let's just check to see if that fuse is still okay. So again, this should be roughly 100 microamps. Looks fine. Alright, let me just check this thing out all the way, and then we'll set up for the next test. Alright, so I've reset our transient generator for 5000 volts peak. Again, this will be 100 microseconds with a 2 ohm source. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. It's interesting, you can see the battery indicator is coming on. And again, let's just try shorting it out. That looks fine. Again, this will be a 1 mega ohm resistor. That looks good. Let's just try it in volts. Again, this will be 5 volts. Let's try it in AC. Again, this will be 2.5 or 2.8. Let's try frequency. Again, this should be 60 hertz. And diode check. This is with a short. And here's a single diode. Looks normal. Let's just try resistance. This should be 100 ohms. Looks fine. And let's go to current. And again, this should be 100 microamps. Again, that was 5000 volts peak. I'll go ahead and finish functional testing it. Kind of bothers me that that battery indicator came on. You can see it's off again. You know, that battery was low when I received the meter. I may have to drop a new one in. Alright, so I've reset our generator for its maximum output voltage. Alright, again, this will be just shy of 6000 volts. It'll be a 100 microsecond full width half height with a 2 ohm source impedance. Okay, that's it. Let's have a quick look. Let's just try it with a 1 mega ohm. Again, this will be roughly 5 volts. Should be roughly 2.8. Let's try frequency. Again, this should be roughly 60 hertz. And again, here is a single diode. And this is with a 100 ohm resistor. And let's see if we finally blew our fuse. So again, this will be 100 microamps. This is the maximum level that I can get out of this transient generator. Again, this is just shy of 6,000 volts. It's about 5.9 or so, 5.8. So let me go ahead and I'll finish functional testing this, and then we'll decide what to do next. Before we do anything else with the meter, let's just retest the EF function. It seems to still work. Let's just try it reading our AC line voltage. You can see it's in low Z mode. It's reading about 118.6. See what happens if we turn it off. You can see it takes a while to, figure out the mode and then auto range. This is probably one of the slowest auto ranging meters that I've looked at. You can see we're in the motorcycle trailer. See, I got a can here of VP race fuel, and this is Q16 this time. Just going to rub a little bit of this on the ANIG meter. And let's try it on the little Brymen as well. Maybe put some on the case. See if we can get the lettering to rub off. Stuff's got a little bit different odor to it. Stinks. Boy, looks good. Look at how soft this makes this. This isn't like I'm using the real sharp part of the knife. That's just that plastic is just melting away. I'm not sure what they're using to make their lenses with. But again, you can see with the little Brymen meter, there's no effect on any of the lettering. Everything is just fine. Well, there you go. I would say if there is a pass-fail criteria, this looks good. Alright, so you can see I have my original transient generator out, along with the oscilloscope and the high voltage probe. Again, because these leads are not detachable, I'm just going to be using these small adapters. I currently have the generator set for 6,000 volts peak. Again, this generator puts out a 50 microsecond full with half height rather than the 100 microseconds that we've been testing with. And again, this generator also uses a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with each mode of the meter. Again, I'll just be flipping the leads to change the polarity. Alright, that's it. Looks like it picks up and open. Again, this should be 100 microamps, so it looks like the fuse is still okay. And again, this will be a single diode. That appears fine. Let's just try it with a 100 ohm resistor. That looks fine. Again, this will be roughly 5 volts. That looks fine. Let's just switch it to AC real quick. And this should be 2.8. That looks fine. And let's just try it with our 1 mega ohm resistor. That looks okay. Alright, so it looks like the meter survived that test. Let me just go ahead and finish functional testing it. Alright, so the little Brymen checks out. We'll just reattach it to our generator. I've restrapped it for 8,000 volts peak. Again, this is a 50 microsecond full width half height with a 2 ohm source impedance. Oh, so something broke down. That's what it looks like on the scope when it breaks. You can see we don't have that nice exponential decay anymore. This is currently set for 100 microseconds per division. You can just see it just went up and dropped right back down when it broke over. That's typically why I leave the scope on here. It's not that I'm concerned about the test setup changing at all. But if something does happen to the meter, it's a pretty good indicator. We'll just start in current because it's in that mode right now. And this will be 100 microamps. Whew. So the fuse is still okay. Let's try shorting our 2 leads. That looks okay. There's a single diode. Wow. Let's try resistance. Here's our 100 ohm. Here's our 50. That looks okay. This should be roughly 5. This should be 2.5. Let's just switch it to AC. Again, this should be 2.8. Oh. Let's try it in frequency. Again, this should be 60 Hertz. Alright, let's just see if it'll pick up our 1 mega ohm. Ha! Let's try it with a 50. 1K. Again, let me just attach it to our AC line output. 117. So it doesn't appear that we've done any permanent damage to it. Let's just take it apart. We'll see what's going on with it. Alright, so looking at the meter, I don't see where it broke over at. It's possible it actually arced across one of the slits. I think that would be the next step, is we can just hook this thing back up. And let's just see if we can detect where it's breaking down at. It should be like right down in here. Well, I saw both spark gaps go, but I wonder if we have to install our rotary switch. And now let's try it. Looks fine. Let's try it in the auto. Well, I'm not really sure where it broke down. It looked like it was in this area right here. I almost wonder if it didn't arc like from here up to here. It's a little difficult to tell. Well, I think that answers it. So the meter is going to break down somewhere around 8,000 volts peak. That's pretty impressive. And of course it didn't electrically damage the meter, but this is what I was saying, like that Unity meter, You know, I gave it some transients and the meter started breaking down pretty early on in the testing, and eventually I started cutting away material to try to increase the clearances, you know, and eventually I did damage the meter. But the fact is when a meter like this breaks down like that, it's pretty much the limit of the meter. Even though the meter may survive the transient, if it were to ever break down like that with a high energy source, that potentially could cause the meter some pretty extensive damage. So I think that's going to be it for our transient testing. Let me go ahead and we'll put the meter back together and I'll functional test it one last time. Dave Jones had put together a pocket meter shootout, and he looked at an AMPROBE as well as a Brymen. They weren't this exact meter, but one of the tests he performed is he twisted the meter. I'll splice that clip into this video so you don't have to hunt it down.
It's exactly the same meter, it's just rebranded AMPROBE, which is actually Fluke. Fluke own AMPROBE, and they're tested to the same standards as regular Fluke meters. And it comes in several different models, and they're quite actually confusing. Now, one problem I have with this, look, I've got that in ohms range. Look what happens if I twist it. It entered volts range. I'm hardly twisting that at all. I'm hardly twisting that, and that is switching between ohms and volts. That is a complete and epic fail. I don't like it's sort of, and the indent is quite reasonable. Put a bit of wiggle on that, it's okay, but just the slightest bend. Unbelievable. That's bad. Let's see if it happens to the AMPROBE. Nope. Nope. Have I got a dud? I might have a dud, but anyway, not impressed.
Alright, so I've removed the case, and you can see I've attached a 500 ohm resistor. And let me just try to twist this. Be a little difficult, but see if I can give you some idea how much I'm bending this. It's a very subjective test. You can see it's not having any effect in that mode. Let's just switch it to the auto mode. And there's our 500 ohm. Again, I'm applying a fair bit of force on this. Put it in DC volt mode. This should be roughly 50 volts. You can see 51.3. Again, let's just try twisting it. I mean, I'm really bending this thing. And you can see it's not having any effect on this at all. I'm a little worried I'm going to bust the case if I push it much further. So yeah, I'm not able to replicate the problem that he's seen with this particular meter. I think that's going to be it for this video. I hope you enjoyed it. Maybe in the future, True, the original poster that started all this, will post again. Maybe he'll provide some additional information that'll help us understand why the 4 meters that he had all failed the same way. So that's going to be it for now. In the next video, we may look at the software that I wrote for this Unity UT181A. Again, that software will allow Labview to interface to this meter through the BLE interface. Well, till the next video. Later.